Hello everybody, I'm Luc Géritz from the University Côte d'Azur in France. Today I will present you a true decentralized implementation of a car crash use case using IoT and blockchain. My colleagues are Roland Crom and Professor François Verdier. So first we introduce the context. So the goal here is to connect vehicles with a decentralized system that is based on blockchain. So we'll define blockchain and other keywords such as smart contracts later on. The challenges of this goal is that the IoT in a car are constrained devices, so yes, they have limited battery, limited memory, connectivity and computation. And the other challenge is that how are we going to scale the blockchain system for this context? So, and also how we're going to identify it and how is the security going on. So also there are two other questions, for example, that are out of scope for this goal. For us, it is, for example, how the car is going to handle the communication because the car is not continuously connected to a network. And another challenge that is out of scope, for example, is that how and what kind of data is going to be sent to the decentralized system and how is privacy going to be handled, the GDPR, etc. So that is not going to be answered in this presentation. We're going to answer the first two questions. So in the related works, we have two main related works. One that is a blockchain-based vehicle infrastructure, where they use smart contracts to digitize a vehicle lifecycle in a secure car smart service book. So in that work, the data is stored locally, is partly stored locally and partly stored in the blockchain. So another work is a forensic study where they have a use case for vehicles that and they want to determine the vulnerable parties for the forensic situation. And in that use case, they use the data hash, and the data hash is sent to the blockchain, and the data itself is being stored in a central database. So we are going to use the same approach than the forensic use case by using the data hash, but we are also going to store the raw data in a decentralized system. So both work describe an ecosystem, but it still lacks of scalability analysis for their implementation and proposal. So next, our use case is Renault's accident use case. So Renault is our industrial partner. It is one of the biggest car manufacturers in France. So the use case is the accident case, as you can see here. When an accident occurs, the vehicle has previously recorded data. So data, for example, such as the odometer, the car speed, the radar, the images around it. And the use case wants to send that data when an accident occurs to a blockchain that has also smart contracts. So the blockchain and the smart contracts will allow to have a collaborative service with an insurance, for example, an expertise, a car mechanic, etc. So what we do here is to take advantage of the blockchain functionalities such as traceability, immutability, decentralization, etc. And the smart contracts are a secure execution of a business logic inside of the blockchain. So we can automate, for example, refunds and automate insurance procedure, etc. So what is blockchain? Blockchain is a distributed peer-to-peer ledger. It has immutable records and it is cryptographically secured. So blockchain provides traceability, as we have seen before. It provides secure records, it provides secure identity, and more. So in this study, we also need to know what is Hyperledger Sautus. Hyperledger Sautus is a private blockchain that is targeting companies. This blockchain is very modular. So as you can see on the graph here, this is the graph of how a Hyperledger Sautus is working. We have a validator node that is one of the peer of the blockchain. And in this validator node, we have a validator that is the core software of this blockchain. Around the validator we have modules, so such as the REST API. The REST API is the interface for the client to the blockchain using HTTP. And we have other modules such as the transaction processors. So transaction processors are analogous to smart contracts. So they contain a business logic, and that business logic is executed when a transaction arrives. There is also a module that is called the consensus engine, and the consensus engine allows Hyperledger Sawtooth to use different kind of consensuses. It is also possible to have custom modules that connect to the interconnect of the validator. We also need to introduce IPFS. We use IPFS as a peer-to-peer distributed file system. It's using direct acyclic graph to link and organize data. We need to notice also in IPFS that the data is identified and located using its hash, and that also not every peer and not every node in IPFS contains the entire database. Not such as the blockchain. Blockchain saves all the data into all the nodes, and with IPFS it saves data in some nodes. So there are also other features that is such as the name system and also HTTP support for IPFS. So why do we want to use Sawtooth and IPFS? So we want to combine the two of them to optimize the blockchain data record storage. We'll talk about that in a few slides. And one other reason to use the combination of those two systems is that they can be deployed in a private network, and that means that we can maintain a certain level of privacy. It is also possible to create a link between the two systems using the Sawtooth modularity. Sawtooth is an enterprise blockchain, so it has enterprise functionalities, and also IPFS has promising scalability for its data storage and data distribution. So in previous work, we have worked on on-chain and off-chain solution, and we have seen that the off-chain solution is the one that we need to use. So this means that in an off-chain solution we have clients. So here the clients are the cars, the vehicle that contains an IoT, and the IoT is going to send the transactions to a blockchain network. So this means that the IoT is not connected also in continue, and that the IoT doesn't store the ledger, the blockchain ledger, and it doesn't also participate in the blockchain consensus. So we have also worked previously on a study of an adaptation of an embedded architecture for Hyperledger Sawtooth application. So the application of that study is the same than the current one, so the use case we saw just previously. And in this study we have built a C++ client. This C++ client, we have also used with that an architecture model of an IoT, so the Raspberry Pi, the BCM 2837, that is written in System C. We did some tests and benchmarks and profiling on the client, and we saw that one of the most used function is an hashing function, and this allows us to have an architecture model in System C of this hashing function and to build simulations. And based on the simulations, we have concluded that it is possible to optimize the client IoT. So next is, why do we want to do this implementation? So we know that blockchain is immutable. This means that every time we send a transaction, the transaction, when it's added to a block, it won't be able to remove it. So it's an append-only database, meaning that if we send huge data to the blockchain, it will store a lot of data also. So this is not really scalable, because we can use a typical example of how the storage is increasing in the blockchain with Bitcoin, where we can see that with only 500 bytes per transaction, we have a blockchain ledger that is now 245 gigabytes after 10 years. And in our use case, a car is going to produce up to megabytes and gigabytes of data. So if we include the video and images, for example, so it is nonsense to actually save that data directly into the blockchain ledger. That's why we propose and implement a distributed solution for this use case. So the deployment and the results. With the implementation, we did a practical combination of Sawtooth and IPFS. So we have here on the graph on the right the blockchain and here IPFS. What is the role of the blockchain? The role of the blockchain is to handle the transactions, it's to handle the smart contract, it also stores and handles the client identity, and it also stores an IoT data IPFS hash. So the IPFS hash, as we have seen in the introduction, it is a hash that references the data location in IPFS. So IPFS is just going to store the raw IoT data. So as you can see on the graph on the structure of our implementation, we have the IoT here that will send transactions, and when the transaction arrives in a node, it will arrive to the REST API, it will be sent to the validator. The validator will pass that on to the transaction processor, and the transaction processor will communicate with the IPFS module that we built, and the IPFS module will send information to IPFS REST API. So this is also an API that we built. And the reason why we want to do this communication between the two systems is to identify and prove that the data is actually coming from an IT, because otherwise IPFS has no idea that the data is actually coming from a verified IoT. So how are we going to do this identification? So we established a protocol of identification between the IoT and the blockchain and IPFS. So how is that going to work? The IoT sends an encrypted data to IPFS. The data can be encrypted into with any kind of encryption, and along with that there is a public key, and this public key will be later on be used for the verification. So the data will wait in IPFS for a signature, and in the meantime the IoT is also going to send a transaction to the blockchain with the data hash and also a data decryption key and a signature. So the signature is actually a signature that is built with the private key of the IoT, a public key of the IoT, and a public key as the message, because we didn't know what was the message, we just chose the public key as a message. So after the transaction arrives in the blockchain, it will go through a validator, it will go into a transaction processor, and then the transaction processor will use IPFS module to communicate the signature and the data decryption key. So once the signature and the data decryption key arrives to IPFS, it will verify the signature with the public key and the public key as a message, and if that matches the public key, then it means that the data is actually proven that the data is coming from an IT. And if that's the case, then it will decrypt the data and store the data into IPFS. Otherwise, the data will just be rejected and deleted from IPFS. So that's how we prove the identification of data coming into IPFS with the blockchain and IPFS. So next, we also have included in the smart contract of Hyperledger Sawtooth, we have included a permission chain. So the permission chain is there to identify the IoT itself. So, and the car and the factory, etc. So we want to identify where the data is coming from and who authorized the data to come into the blockchain. So the permission chain works where in a way that the idea is to have always a high authority that allows a lower authority to exist and send transactions. In a simple way, we have here, as you can see in the business logic, we have a blockchain administrator that will allow a factory to exist in the blockchain state. And the factory, once it's been added into the blockchain, will be allowed to create a transaction to create a new car in the blockchain network. And once the car has been added into the blockchain state, then the car is able to send valid transactions along with the driver identity to the blockchain network. So next, we also studied two consensuses with 5-node network. So we studied the practical Byzantine fault tolerance and the proof of elapsed time consensus. So with the practical Byzantine fault tolerance, it shows that after 10,000 transactions, with an average of 2.7 transactions per second, the system will, the blockchain will start to reject a huge amount of transactions. So we stopped at 10,000 transactions. As you can see on the graph here, where the number of transactions is increasing, and we have the number of committed transactions and the number of rejected transactions, you can see that here the commit rate is the same with and without IPFS module. So this graph is showing the proof of the practical Byzantine fault tolerance by using the IPFS module and by not using the IPFS module in the Hyperledger Sawtooth blockchain. So you can see here that the commit rate is always almost the same than when using IPFS module and without. You can see also that the reject rate with and without the IPFS module is almost the same also. But you can see that the execution time in the transaction processor is in an average always higher than without the IPFS module. So we see actually an increase of 10 to 100 millisecond execution time in the transaction processor, but it still has no influence on the number of transactions that has been validated, so the transaction validation rate. Also, we see that with the proof of elapsed time consensus, after 5,000 transactions, we observe that the blockchain network will start to not be stable anymore, and it will start to halt, and nodes will be rejected, etc. And we have multiple reasons and multiple other papers that shows the same result, that after a certain number of transactions, the proof of elapsed time consensus doesn't really work anymore. So there are multiple reasons. Maybe it's the default configuration. Say the two papers here have used the default configuration and show exactly the same, almost exactly the same results. It can also be a hardware problem, or it can be also a problem coming from the number of nodes. So next, we have studied now the IPFS and blockchain implementation, but we also need to study the IoT implementation, the client. So in the client, we have used the same program than in the previous work, the C++ Sawtooth client, and we integrated the necessary functions to include the IPFS hash and sending the data to IPFS, etc. And we saw that the SHA-256 hash is used multiple times. It's used in the transaction to sign the transactions. It's also used in IPFS to build the IPFS hash. And as you can see here in the protocol, in the procedure for how the data has been handled in the IoT, so we have the sensor that creates the data. Then we have the data that is going through the IPFS hash. And once the IPFS hash, we can send the raw data to IPFS along with the public key, as we have seen in the protocol before. And also, it will then build the transaction with that hash, and along with, of course, other information in the transaction, it will send that to the blockchain to Sawtooth. So we have studied here the latency of the program, and we wanted to analyze how the hashing function latency is increased when the data size increases. So we have seen that when the data size increases, the total execution time increases, of course, and we have also the hash that is always still one of the most used function, and we have observed also that the hash creation latency is always getting more and more significant. You can see that on the graph here. And based on the previous research, we have seen that it is possible to have hardware acceleration on this kind of function. So in conclusion, we have deployed a practical and scalable vehicle infrastructure that is able to record data on Hyperledger Sautus, reduced the recorded data size in the blockchain by using only hashes, and we also added into our implementation an IoT identification system with a protocol, and we also added a permission inside of the smart contract. So we also studied two consensus, the practical Byzantine fault tolerance and the proof of elapsed-time consensus with 5 nodes. We have seen that the practical Byzantine fault tolerance is limited after 10,000 transactions with an average of 2.7 transactions per second, and we have seen that the proof of elapsed-time is less stable than the Byzantine fault tolerance. We have also analyzed the latency of our IPFS module inside of the transaction processor as a module in Sautus, and we have seen that there is no major impact on the transaction validation rate with and without using our IPFS module. And finally, on the IoT, we have seen that it is possible to include a hardware accelerator for a hashing computation, and to thus also decrease the latency of the IoT using that hardware accelerator. In future works, we want to improve the configuration of Hyperledger Sautus. The goal is to increase the number of transactions per second, but also to increase the threshold of that 10,000 transaction limit. So we want to increase that and have no limit of transactions. Also, we want to test other blockchain technologies, maybe with adding a decentralized application approach. And finally, in future works, we want to use dedicated IoT architecture modeling using IoT hardware accelerators. Thank you for your attention. Bye.